Thank you. As was just mentioned, I'll be talking about laboratory experiments investigating entrainment by debris flows. So just a brief overview of how this will go. I'll touch on some background about debris flows and how erosion is an important factor, and then the experiments that we performed and some of our results. So first of all, why is entrainment important? Debris flows begin, as has been mentioned many times, with the destabilization of sediment, water, and rock. And as they travel down the slope, they have the capability to increase dramatically with size, increase dramatically in size due to entrainment of bed materials. And this entrainment is suspected to play a major role in flow dynamics and partially in making flows that are much bigger and faster and more dangerous, and also, as a result, more geologically impactful. And the eventual goal of this is to have a better idea of how to be prepared for events, of debris flow events for hazard mitigation. So this topic has been approached in a number of different ways. One is with experimental studies, which are very helpful in identifying some key parameters of interest. Some experimental studies have highlighted erosional effects on mobility, which is partially motivated our study of entrainment, since instantaneous entrainment is what's going to be is suspected to play a role in mobility, and that's a very important factor as we've seen with the Oso disaster. Some other important parameters controlling erosion have been moisture, sediment concentration, and particle size effects. Some field results listed here are a couple of field stations of note due to their measurement capabilities. It should be noted that the references listed here is just a sample. There's been a lot of work on this field. Two specific studies of note would be by Berger et al. In 2011, where they were looking at entrainment in normal and shear stresses, and saw that entrainment was particularly well correlated with the highly fluctuating granular front. And also by another one by McCoy et al. In 2012, where they were looking at entrainment and also the volumetric water concentration, and there they saw that entrainment was strongly correlated with the water content of the bed sediments prior to the debris flow events, which leads us to wonder what exactly is controlling the entrainment rate. There's a number of possibilities, and so what we set out to do was investigate some of these through some systematic laboratory scale flume experiments. So here's a sketch of our experimental setup. We've got a debris flow flume with both an erodible and rigid portion of the bed. The value in that is that when the debris flow is released, it'll be hitting the bed at the same angle of inclination as the erodible section. And we can vary the angle of inclination, and we've used all spherical particles of either glass or zirconium silicate beads. So just for a brief procedure, we start with filling the erodible bed and then raising it to our desired angle, and then releasing the particles and triggering a couple high-speed cameras, pore pressure sensor, and stress sensor. These are all set up in such a way that we have them time-linked so that we can see what's happening with pore pressure or whatnot as compared to how far into the flow we are. And we also measure the mass of the effluent out. So with that, we can be finding out about total net erosion, and also with using our high-speed imaging to get data about the instantaneous entrainment and other kinematics, and then also getting data about pore pressure and the stress sensors. With our high-speed camera, we've got two cameras, one for a wide-angle view for the general behavior of the flow, and another for a close-up for entrainment analysis. So here we've got this will start, hopefully. We can see our wide-angle view. This is at an angle of 24 degrees. So you can see gravity pointing in roughly this direction. We can see the very sparse flow coming in initially and hitting the bed. It's very energetic, but it's not really making a big difference in terms of entraining particles. But as we skip later on and the flow becomes more dense, we can start to see the mass of the bed being entrained and starting to move. We also would like to note there is an edge effect up here with where the rigid bed ends and the erodible bed begins, which is why with our instantaneous entrainment, we focus farther down the flume here so that we can avoid such edge effects. So we can see also another example, again at 24 degrees, we got again this very sparse granular flow coming in, and as we go on, we can see how more of the bed gets entrained and pulled into motion later on in the flow. And we'll go over this a little more later in the presentation. So we've approached this from two angles. One is with net erosion and then with instantaneous erosion. So we'll start with the net. One thing that we've found is the sensitivity of the results to our initial conditions. As we can see here, our bottom axis is the number of runs performed, and then we've got the eroded mass. And as we can see with these red dots, when we recharge the bed but don't completely reset it, we have somewhat of an aging effect, and so the bed becomes more fragile with time and have increasing amounts of erosion. However, when we are careful to reset the bed before each run, we get much more consistent, reproducible results. Some of these results that we've seen in terms of net erosion for uniform systems, we've got 5 millimeter particles. Here we've got the angle of inclination and then the relative erosion. One thing we can see here is that for any particular system, our erosion rates are increasing as our particle size is increasing. We can see it especially clear here with 2 millimeter particles and 5 millimeter particles. Another interesting result we've seen is that as our angle of inclination increases, the relative relative erosion is also increasing. And this supports the framework that's been proposed by others, that there's somewhat of a neutral angle, that after a debris flow event, if our angle of inclination is higher, that there'll be more erosion to bring the bed back to this neutral angle, or if we're at a lower angle, there'll be deposition to bring it back to a neutral angle. And this is interesting, but we're also, in order to understand things about mobility, we need to look more at instantaneous entrainment. So moving forward into that, here we've got some more of this high-speed camera imaging, and we can see how the system is changing with time. And then also we'll go back to our video of our high-speed flow. So here we can see we've got particles in motion up here and particles that are not in motion down below. And we can see as we go through, we've got a non-physical boundary that's moving down with time. Initially, we have this, it would be a line up here where there's particles moving and particles not. But over time, this is moving down. This is what we're calling the entrainment rate. Well, this is where the entrainment is happening. So particles that were initially not moving are now being brought into motion by the flow overcoming. And so using our high-speed camera, we're able to get velocity profiles so that we can measure the rate at which this line is moving down over time and get an estimate of the erosion rate of the system. So here we've got just 3 example time steps of this. At the very beginning, 0 seconds into the flow, 1 second into the flow, about the middle, and then 2 seconds in. Down here in the bottom, we've got the horizontal velocity versus the height, and then the solid fraction, or just a measurement of the density of the flow, again with respect to height. So up at the top, this is where we don't have a lot of particles. It's very sparse flow, and down at the bottom, it's much more dense, where we actually have the whole system. As we can see here, especially in the 1 and 2 seconds time steps shown, the velocity profile has an exponential decay, as has been suggested by other studies. And we can see, so what we've done in order to find that entrainment rate, we've done an exponential fit and then set a critical velocity, and saying that below 0.01 meters per second, we're going to say that the particles are no longer in motion. And so using that exponential fit, we can find at what height that occurs at each time step, and then track that over the course of a debris flow, and then find a rate from that using a time average. So here we have, for 4 different cases, our entrainment. So here, this 0 marks the initial position of the bed. So this would be where we have motion or no motion. And so we see how that decreases, that non-physical boundary moves down through the system over time. Here we've got 4 cases with 23 degrees, 23.5, 24, and 24.5, and we'll go into why this one is lower than the other ones in a little bit. And then we did some time averaging. So here we've got each line represents time, the average slope, so the entrainment rate over a half-second interval. The red is 0.5 to 1 seconds, and then continue on from there. We ignore 0 seconds to a half second because of that very sparse granular flow, the very sparse beginning of the granular flow. Our tracking tracking algorithm is calibrated for the denser portion of the flow, and so we don't. These results at the very beginning are not very reliable, so we focus more on where we actually have the dense flow coming in. So we can see that as our angle of inclination increases, our entrainment rate is going up. Here we get to 24 degrees, but then at 24.5 degrees, our entrainment rates are going down again. So to understand a little bit more of this, we also are looking at some other physical properties, such as, well, I guess first we're going to look at how this relates to our net entrainment. Pardon me. So we can see here we've got our angle of inclination and our entrainment rate, our instantaneous entrainment rates. the average for each of those time steps, as were just shown, and then the net erosion. And we can see that there is a nice monotonic increase, increasing trend for the 23 to 24 degrees that our entrainment rates are increasing, and so our net entrainment. And then again, to understand a little bit more about this, we look at shear stress, another property of the flow. In order to do this, we used depth slope product just as an initial method for finding the shear stress. So we've got density of the particles times the solid fraction to get the overall density of the flow, and gravity, and the height and the slope. The height was determined, again, using our solid fraction and our horizontal velocity profiles. So using our solid fraction, we can get an upper boundary of where our flow is sufficiently dense to say that this is actually the flowing layer instead of just sparse particles bouncing around on the top or no flow at all. And then we can find a lower boundary using that exponential fit to find out where the bottom of our flowing layer is, and that becomes our H value. From there, we can see that we have our shear stress profile for each of the 4 cases that we saw for entrainment rates. And we can compare these with the entrainment and see something interesting. We noted earlier how this 24.5 degree case has a lower entrainment and lower entrainment rates than we've seen with the net entrainment, but we also see that there's less shear stress in this case as well. So looking at that, we've got time averaging of the shear stress again over those half-second intervals, and then also a time average rate of entrainment. And then we've got a parametric plot here. We've got shear stress on one axis and the entrainment rate on the other, and we can see here that there's not a simple relationship between the shear stress and the entrainment rate, suggesting that there's other factors going on and that we need to continue to investigate these parameters. So to summarize, we've done a series of laboratory experiments to investigate erosion and its dependence on the diameter of particles, on shear stress, and also how it varies with angle of inclination. Our net erosion results have indicated a linear dependence on the angle of inclination theta and the neutral angle theta sub n. However, our erosion rate, E dot, is not the same. When we're close to the neutral angle, we see a monotonic increase of the erosion rate as the angle of inclination is increasing. However, when we get to higher angles of inclination, this trend begins to decrease. Erosion increases, the total erosion increases with our increasing flow shear stress. However, our erosion rate does not have such a simple monotonic increasing with the shear stress. So in moving forward, we're going to be looking at the effect of fluids on the systems, as well as the effect of granulating stresses, the effect of fluctuating stresses or the granular temperature, and also more complex mixtures. Thank you.
Thank you. We have time for questions.
A lot of debris flows already have the chute between episodes. It fills in with debris.
Mm-hmm.
So it's not really eroding. What insights can you share what we usually see in our cases?
In those events, as I might have glossed over it too quickly, so I apologize for that, but when we're talking about with the entrainment, a lot of that is picking up those loose bed sediments that are in the debris flow chutes from previous events.
I was wondering why, for your plot that had a erosion rate as a function of the flume incline,
Okay.
if you had any idea why you were having such large dispersion for a given inclination.
Maybe I'll just go back to that and see what exactly.
So that
This one, yeah.
Yeah, so you're for a given angle, your dispersion, your results is large, like for the green or the red dots.
Oh yeah, those are
Do you have a
the.
sense why that is?
Yeah, that goes.
Repeat the question.
Yes, so the question is why there's a large dispersion with the entrainment, I believe with the entrainment rate, so the red and the green dots, for example, for a given angle. And so that's because the red, green, and blue and purple dots plotted here are those the time average entrainment rates. So those vary as we can see. So those are varying with time. So for different sections of the flow, it's changing. Yeah. Mm-hmm. Yes.
just so people can hear me. Your observations are really interesting, and obviously, when viewed at the grain scale, you see this exponential-like profile associated with the propagation of what you might call an entrainment front. Mm-hmm. From the standpoint of continuum mechanical modeling of debris flows, assuming you wanted to model large-scale flows and so forth, it's generally necessary to approximate that as a sharp front, an actual discontinuity. Okay. And based on your observations, do you think that's a reasonable thing to do, to approximate it as an actual velocity discontinuity?
Potentially. I guess I have not seen that. Most of what I've seen is has been where there is that exponential decay, but I think that'd be something to look into. Thank you.